Consider a long, thin wire rod of negligible mass resting on a fulcrum. Suppose we place the object having mass of m1 and m2 at the distance of d1 and d2 from the fulcrum or from equilibrium, respectively. The mass balance each other if and only if m1 times d1 equal to m2 times d2. Suppose that the center of mass x bar is the fulcrum and the mass are located at distance x1 and x2 respectively. Then the distance d1 is x bar minus x1 and the distance d2 is x bar minus x2. Substitute that into our formula, solve for x bar. We get x1, m1 times x1 plus m2 times x2 divided by m1 plus m2. This idea is not limited to just 2-point mass. In general, if we have n mass, the mass m1, m2, so on and so forth to m sub n are placed on the number line at the points x1, x2, and xn, so on and so forth, respectively. And the center of mass is given by the total of the mass times the distance divided by the total of the mass. So here we got a theorem. Let m1, m2, m sub n be point mass placed on a number line at point x1, x2 to xn respectively, and let n equal to the sum of the mass, the total mass of the system. Then the moment of the system with respect to the origin is given by capital M equal to the total of m times the distance. And the center of the mass is given by capital M divided by small m. We can generalize this concept to find the center of mass of a system on a point mass in the plane. Let m1 be the point mass located at the point x1 and x2 in the plane. Then the moment m sub x of the mass with respect to the x-axis is given by m sub x equal m1 times y sub 1. So why is it times y sub 1? Because the distance of m sub 1 to the x-axis, the distance of m sub 1 to the x-axis is actually y sub 1. Okay. Similarly, the moment y sub m sub y with respect to the y-axis is given by m sub y equal m1 times x sub 1. Again, because the distance from m1 to the y-axis is x sub 1. So here we got a theorem. Let the point x1, y1, x2, y2, x sub n, y sub n be the location of the point mass m sub 1, m sub 2, m sub n respectively, and let m equal the total mass of the system. Then the moment x sub m sub x and m sub y of the system with respect to x and y are given by the formula. Also, the coordinate of the center of mass x bar, y bar equal the moment of y divided by total of mass, and that y bar is the moment of x divided by m. Suppose 3-point mass are placed on a number line as follows. Assume the coordinate as in center. M sub 1 equal 5 km placed at the point negative 2, 3. M sub 3 at 3 km placed at 2, 3. N sub 3 is 2 km and placed at negative 2, negative 3. And we want to find the center of mass of the system. First, we will find the total mass of the system. The total mass M equal the sum I equal 1 to 3 of m sub I, that is 5 plus 3 plus 2 make 10 kilogram. The next thing, we will find the moment with respect to x and y axis. m sub y equal the sum from I equal 1 to 3 of m sub I times x sub I. So now we have 5 times negative 2 plus 3 times 2 plus 2 times negative 3, and that is negative 10. The moment with respect to x So now we can find the center of the mass system. X bar is equal to the moment with respect to y divided by m, and that is negative 10 over 10, that is negative 1. Y bar is the moment with respect to x divided by m, that is 20 divided 10, that is 2. So the center of mass is the point negative 1, 2. So let's talk about center of mass on a thin plate. The symmetry principle. If a region R is symmetric about a line L, then the centroid of R lies on L. So the centroid of R lie on L. Okay. It makes sense, right? If you have, say, for a example, say we have a triangle that is isosceles triangle with symmetric with respect to the y-axis, then the centroid of the triangle is lying somewhere on this y-axis. So that's what the symmetric principle says. Let R denote a region bounded by above by the graph of a continuous function f of x, below by the x-axis, and on the left and right by the line x equal a and x equal b respectively. Let rows denote the density of the associated lamina. Then we can make the following statement. The mass of the lamina equal to rows times the integral from a to b of f of x dx. The moment mx and my is also given by the formulas. And we can find the coordinate of the center of mass using the given formulas. Okay. So let R be the region bounded by the graph of the function f of x equal to x squared, and below by the x-axis over the interval 0, 2, assuming that the density equal 1, and let's find the centroid of the region. First, let's calculate the mass of the lamina. So m equal rho, that is 1, for the integral from 0 to 2 of x squared dx. That is 1/3 x to the third, evaluate from 0 to 2, and that is a over 3. The moment m of x and m of y of the lamina with respect to x and y. So the moment with respect to x, that is integral from 0 to 2 of x squared that make x to the 4 divided by 2 dx. So this is 1/5 times 1/2 x to the 5th from evaluate from 0 to 2. So this is 110 times 32. 16 over 5. The moment with respect to y. So x times f of x. So x times x squared make x to the third. So 1/4 x to the third, evaluate from 0 to 2. 1/4 times x to the fourth. (16 over 4), that is 4. Now that we have the moment with respect to x and moment with respect to y, we also have the total mass. We can find the center. X bar is equal to 4 divided by 1/3. So that 4 times 3, 8. So 3 over 2. Y bar equal to x, that is 16 over 5. Divided by the mass, 8 over 3. So 16 over 5 times 3 over 8. That is 6 over 5. So the center is 3 over 2. 6 over 5. So what happens if we have if the region is bounded by two functions? Okay. So let R be the region bounded above by the graph of the function 6x squared and below by the graph of the function 3 minus 2x. Assuming that rho is equal to 1, we want to find the center of the region. We first need to find the mass of the lamina. So the mass is equal to rho times the integral from a to b of f of x minus g of x dx, assuming that f of x is the region that is above. Okay. So first thing first, we need to figure out what is our a and b. We can do that by letting g of x equal to f of x and solve for x in that case. So we have 6 minus x squared equals 3 minus 2x. Factor. So the mass is the integral from -1 to 3, rho equal 1, of 6 minus x squared minus 3 minus 2x dx. Okay. And this is evaluate this interval, we get 32 over 3. Now the next thing we need to do is to calculate the moment with respect to x and moment with respect to y. The moment with respect to x is given by rho, the integral from a to b, of 1/2 f of x squared minus g of x squared dx. Okay. So let's go ahead and put everything we have into this formula. We know that the integral is from -1 to 3. We take the 1/2 out front. F of x squared is equal to 36 minus 12x squared plus x to the 4 minus g of x squared. G of x squared is 9 minus 12x plus 4x squared. And this is with respect to x, so dx. Simplify. And we evaluate this from -1 to 2, we get 832 over 15. Now let's go ahead and calculate the moment with respect to m. That is rho times the integral from a to b of x times the difference of f of x minus g of x dx. So then we have the integral from -1 to 3 of x times 6 minus x squared minus (3 minus 2x) dx. We simplify this and evaluate the integral. We get 32 over 3. So then the centroid x bar is equal to my divided by m. That is 32 over 3 divided by 32 over 3. That is 1. Y bar equal mx divided m. That is 832 over 15 divide 32 over 3. And let's go ahead and simplify this fraction. We get 26 over 5. So that is our centroid.